All right. Hello, everyone. This is the first of two videos during which I will try and give a gentle introduction to dilation surfaces. Okay, so in this series of videos, I won't be advertising any particular piece of work or theorem, but instead I will try and give you some motivation and somewhat formal definitions of the objects and tools that you might want to know if you want to think or work with these objects. Maybe try and give some philosophy of how things should work. Okay, so maybe I will start with showing you what a dilation surface is in a very informal way. So it's just a polygon with a bunch of sides glued together. So hopefully they'll convince you that these are objects that are easily apprehensible. Okay, so the program for today is I will spend at least half of this video telling you about some motivation that come from smooth dynamics. So I'm not going to assume that anyone's an expert in smooth dynamics. I'll probably work with some rather simple example and try to illustrate some phenomenon that might be known to specialists, but that give sort of a way into the world of dilation surfaces, which are essentially geometric objects, but at least in my view, what makes them like so special and interesting is because they bear this connection with dynamics and this the interplay that is very nice. Okay, so let's start with smooth dynamics, and like to begin with, I wanted to recall the quadratic family that you might have come across, as it is a very popular example, and it yields those very nice picture. This is the Mandelbrot set. So the quadratic family is just a unison family of maps, z maps to z squared plus c. There are as many such maps as there are complex numbers, and so they're parameterized by the complex plane. And if you've seen that, people try and understand what happens if you start from any point z0 and you start iterating fc. And depending on the initial value of c, you can see different type of behaviors. And somehow, so again, I don't want to say anything precise about this, but this picture, the famous Mandelbrot says, is something that reflects different type of dynamical behaviors when you iterate those maps. So the Mandelbrot set represents the parameter space. So to each point in the Mandelbrot set corresponds a parameter c, and it gets a color depending on what you see when you start iterating this map f of c. And the only reason why I wanted to mention this is that maybe you will agree that this family is a fairly simple family of dynamical systems, at least in terms of how to define it. You don't need more than a degree 2 polynomial, and it yields this rather complicated figure. And maybe if you know a bit more about the history of this problem, this is a very complicated problem. Understanding the shape of this Mandelbrot set and understanding what happens when you work with this family has sparked a lot of very nice work that spans like several decades, and to this day this Mandelbrot set is not fully understood, in the sense that people can't really tell what happens in some very deep areas of this set. So you say something is deep, you have those little islands, and you can move from a central one to a peripheral one and keep going deeper and deeper, and people don't really understand what necessarily happens in the limit. And so the point that I want to make is that you can start with some, at least in smooth dynamics, you can start with very simple objects, and they yield like some very complicated pictures that is quite difficult to analyze. So you shouldn't be ashamed of working with very low dimensional, very simple examples, because they're already quite hard to understand. Yeah, the general principle when you do maths, if you can't understand like the simplest examples, there's no need to do anything more complicated, because there's very little chance that you'll be able to do anything. Okay, so the general theme from smooth dynamics that is going to drive me here is the following. So when you have a a family of dynamical systems, you want to know, well, maybe you can't describe every single element, but you want to say what's typical, what are you at risk of seeing if you were to choose something randomly. So then you'd have to define it. Everything is very philosophical here, what randomly means, but it's some particular like concrete instances, as in the quadratic family, for instance. You've got a parameter space that's very nice, and randomly can mean with respect to a natural measure, for instance, the Lebesgue measure on the set of parameters, or for some dense set, or for something. So if you take a more general parameter family of dynamical systems, so you have those phi p, where p is a parameter that lies in a capital P, which is going to be a parameter space. So you'd hope that this parameter space has a nice structure, and they're all dynamical systems of the same nature. So maybe in general they're going to be continuous, maybe differentiable. And you want to understand what happens for a typical P in this parameter space. There are two competing notions of typicality that's that are commonly accepted. So there is one that is more topological. So I was referring to denseness. So people say that you're topologically generic if, I mean, a property. So for instance, the dynamical system is chaotic, whatever that means, or minimal, or has a periodic orbit. A property like that is topologically generic if it holds for a G delta dense set of parameters in P, and say it's probabilistically or measure theoretically generic if it holds for a full measure set of parameters in P with respect to a natural measure. So you'd expect P to be a manifold, and the natural measure to be something that's pretty much the Lebesgue measure. People would argue that the second notion, the probabilistic one, is the one that makes more sense from a physical point of view, because when you pick something at random, you usually do it with respect to a measure, whereas the topological notion has the maybe disadvantage that, for instance, you have in R open and dense set which are not a full measure. If you take the complement of a thick Cantor set, for instance, it's going to be open dense, but when you pick something at random with respect to the Lebesgue measure, might not see this like all the time. So it's probably a problem. But maybe this notion is more flexible. Anyway, I don't want to linger too much on that. So let's just see how this works on very simple examples that you might all know. So taking a very simple, the simplest, maybe arguably a family of dynamical systems that you can think of, you take the circle and you take rotation. The circle is R mod Z, and you take the X plus alpha, and you reduce mod 1. So this gives you, again, a one parameter family of nice dynamical systems. You might ask the question, well, what is the typical behavior in alpha, in the parameter alpha? And this is it's an easy exercise to see that if alpha is a rational number, then this map is going to be periodic, and the period is going to, by periodic I mean that a certain power is going to be the identity, so every single orbit is going to be periodic. And if alpha is irrational, then every single orbit is going to be dense. And if you're a like dynamical system, you say that this dynamical system is minimal. Sorry, took my charger. And yes, and so in that case, the, let's say, typical behavior in the sense of the Lebesgue measure is going to be minimality, because you know that irrational numbers are full measure in the sense of real numbers. And so we're able to answer the question, but you would argue that this somehow family is very simple. These maps are all isometries, so it really constrains the geometry and the dynamics, and makes for an analysis that's almost too simple in the sense that it reduces to almost to number theory or combinatorics. And a physical system is going to have some non-linearity somehow. So if you're really interested in like pure dynamical system type of questions, you want to go beyond this simple family. So again, I don't want to complicate too much, and I don't want to consider a simple family, but where I see it's a different behavior. So what I do is I just take the family of rotation, and I introduce a small perturbation by the simplest one periodic function that I know. It's the sign. So I add epsilon times the sign. So you have to think of epsilon as a very, very small quantity. And I want to understand what happens. And in that case, it's not so clear because I can't make an analysis of R alpha epsilon based on combinatorics or number theory. It doesn't completely relate to alpha or epsilon. The sign is a transcendental function. So I need to appeal to new methods somehow. And you still ask the question. So now I have a parameter space which is two-dimensional, alpha and epsilon. What is the generic behavior? So it's not an easy question, and I just want to start by making the following remark. So it's at the level of the structural theory of so-called diffeomorphisms that has been worked out with the theory of the rotation number. What you can see is that you don't have that many options in terms of potential behavior. Either you have periodic orbits, and your system is essentially eventually periodic. You have maybe a finite or infinite number of periodic orbits, and every orbit that is not periodic sort of limits onto this periodic orbit. This can be made rigorous, and maybe I leave it as an exercise for you to do. So, or it is minimal, as the rotation of angle alpha irrational is, meaning that every single orbit is dense. If you know the theory of the rotation number, I've expressed that on the slides in terms of the rotation number. Okay, so now what we want to try and understand is what of these two competing behaviors prevails. And okay, so maybe I'm going to draw the parameter space. So this is it's actually a famous picture. I took it from Wikipedia, and it's not maybe the nicest that you can find, but at least it works for a basic explanation. So what I'm going to do to illustrate the general phenomenon that's going to take place here is I'm going to focus near parameter alpha epsilon is equal to 0, 0. So I can freeze alpha to be equal to 0 in this formula. And what I'm working with is the map x maps to x plus epsilon sine 2 by x. And you can check that this map has a fixed point at 0, because sine of 0 is equal to 0. Okay, but the difference that when epsilon's different from 0, if you compute the derivative at this fixed point, it's not going to be equal to 1 anymore. And this is an easy exercise in function theory, is that when you have a fixed point and that the derivative at this fixed point is different from 1, well, this fixed point is stable in the sense that if you move your map a bit in the space of smooth functions, then it's still going to have a fixed point near 0. Maybe the fixed point is going to move a bit, but basically, because if you take your map or its inverse, you're going to see some contraction if the derivative is different from 1. And if you move your map a bit, the contraction is going to survive, and essentially, you can use a contraction mapping theorem to see that the fixed point is surviving. So it's a nice thing. So that tells you that essentially when you go up in the epsilon thing, the derivative is going to change. It's going to be equal to 1. And now I can go in every direction, and I'm going to see this fixed point persisting. So I have this and that's what Arnold, who was the first to investigate this phenomenon, called a tongue. And you see that you have a tongue where you have a fixed point, and it survives, and it's an open set. Okay, and what I claim is that you can play this little game at every rational number, and you replace a fixed point by a periodic orbit of order the denominator of the rational number that you start working with. And every time you're going to see this little tongue that's getting wider and wider as epsilon grows bigger, and so this sort of singles out the line epsilon is equal to 0 as very special, because when you look at nonlinear slices, now a fixed epsilon is equal to a positive number, and I vary alpha, then whenever I see a periodic orbit, I don't move from a periodic orbit to a rational number. I stay, there's a locking, a people would call that a mode locking type of phenomenon where periodic orbit survives. And what you see, because rational numbers are dense, what you're actually going to see is that the set of numbers for which you don't have a periodic orbit is going to be a counter set, and the complement of this counter set is going to be little open set, a union of open set where you have periodic orbits. Okay, so this is the picture. I mean, you have to work a bit to make everything rigorous, but it's not much harder than what I've explained. Like, there's not much more maths involved. Okay, so I give a definition because it's going to be more convenient for me to talk in those terms in the sequel. I said a map, in that case, a circle diffeomorphisms, but I'm going to extend that to a lot more one-dimensional maps, is more scale or asymptotically periodic if you only have periodic orbits and they drive the entire dynamics. So if you take any single point, its orbit is going to limit onto a periodic orbit. So the examples that we see in the tongs are more small. Okay, and the theorem of Arnold is that in this parameter space, because of the little reasoning that I've explained, maybe you need a bit more time to make sense of that, but essentially I've said everything, is that this small subspace is open and dense. It's open because the little property that I've explained, that it survives small perturbations because of this contraction mapping theorem, and it's dense because essentially rational numbers are dense in irrational numbers. And what's amusing is that the complements, which I'm not sure I've proved, but I have hinted at a proof that shows that it's a counter set, has positive measure. So there is a competition between these two behaviors. So because an open set has positive measure, then you have positive measure, set of positive measure where things are simple. They have only periodic orbits are driving the dynamics, but there's also a positive measure counter-like, which is the product of a counter set with an interval that has positive measure where you see minimal behavior. Again, I repeat, minimal means all orbits are dense. Okay, so this is a nice theorem, and it was generalized by Herman in 1977 to show that any actually one parameter family of circle diffeomorphisms displays that behavior. There's a formal statement here, but basically you have this coexistence between the two potential behaviors when you work with circle diffeomorphism. Okay, so now, as I was saying, no shame in analyzing simple examples. I take a piecewise affine function. I mean, you'd agree that affine maps are probably the simplest one after isometries, and we've already dealt with isometries for rotation. So I'm working with this map, which is a bijection of the interval that is piecewise affine, and you have 4 discontinuities. Okay, this is an affine interval exchange map, and simple way to make a parameter family with this function. I mean, I take this map T and I post-compose it by rotation of angle alpha. So I take x maps to Tx plus alpha, and I get one parameter family of maps. And so you can ask the question, what happens here? And it's slightly more complicated to analyze because I don't have a ready theory for the rotation number. But what I can show is show you a plot of orbits depending on the parameter. So on the x-axis, I've got alpha, the parameter, and on the y-axis, I've got let's say I take an orbit, I fix alpha, and I take an accumulation, the set of accumulation point of a typical orbit. So essentially, for instance, if I take this parameter here at 0.12, I see that I have what seems to be a rather long periodic orbit. I have a shorter one here, for instance. That would be, well, something in between 0.12 and 0.whatever. And what I see is that when I move around, it seems that the structure of periodic orbits complicates, and you tend to accumulate on things that are very complicated. It's quite hard to tell, and you could run like some more refined numerical simulation. Maybe that would tell you something. The only point I want to make here is that there is some variation when I move alpha, and it's not so clear what happens. I have periodic orbits, and I have more complicated things. Okay. So that's the thing I want to analyze. And here again, you might ask the question, well, you see that those periodic orbits tend to form open set, right? I mean, they're stable and you see it moving a bit. So again, you can ask the question, well, the space of where you have periodic orbits seems to be open. I think if you believe that everything that's sort of stuck in between some complicated zone, you still see very, very long periodic orbit, you can sort of believe that it's dense. They've got an open dense set. I would say how much space does it take measure-wise? And a theorem that you can prove using geometric methods, and I think I'll go back to that in a latter part of the talk, is that actually in that case, for almost every parameter, then T alpha is Morse-Male, meaning that you have finitely many periodic orbits that drive the entire dynamic. And this is something that will have some geometric meaning at some point. So I'm just going to leave it there. One of the main conjectures that I think one can isolate in this field is that we should expect that almost every affine interval exchange transformation is Morse-Male. So affine interval exchange transformation is just a piecewise affine bijection of the interval. So contrast with the circle diffeomorphism case. So again, like these might sound as you know, specialist sort of distinctions. Why would you study those affine interval exchange maps instead of circle diffeomorphism, etc.? And it's true, it is, but still, they're simpler objects, and you might find them interesting. Anyway, so I mean, yeah, I think that to sum up, what we want to understand is what happens in some parameter families. It's hard to make a case for that type of dynamical system instead of another. Probably sometimes you would go for this one because you have a good idea how to tackle the question. And it's the case for those piecewise affine maps. And so that's why I'm going to focus on those and introduce some geometry to study them. But you could do that with many other things. And it's actually very interesting. And we want to understand that what happens in a probabilistic sense, because I think it has like more sense at a physical level, and you have this competition between things with essentially periodic orbits, Morse-Male, and things with more complicated orbits, probably minimal orbits are dense, and that's about it. Okay, so now I'm going to introduce the geometric objects. That's all for the dynamics. There will be some dynamics coming back, but it's never going to be more complicated than what we've discussed in this first part. So if you've borne with me up until there, you should be fine for the rest. So now I'm just going to give definitions, and you choose the one that you prefer, because there are many different ways to think of those dilation surfaces. But it's the space, that's a topological surface that you obtain by gluing together Euclidean polygons along parallel sides. If you've already seen a translation surface, just relax the condition on the gluing, and you ask for sides to be parallel and not same length. So this is an example. Another definition, if you like something very formal in the sense of GX structure, is a map with an atlas of charts for which transition maps are affine with a real linear path. And then you have singularity, so you have to be a bit careful what happens to account for the vertices of the polygons that you draw. And again, I can let you work out what kind of singularities you need to allow. Another example, so you get interesting dilation tori, which wouldn't be the case in translation surface theory. And if you really like an algebraic geometric definition, well, you can say that a dilation surface is a Riemann surface with a holomorphic one form with values in a flat line bundle. Probably just not it's not the most handy to start work, to begin working. Anyway, so now again, I need to recall a concept of, let's say, the crossroad of dynamical systems in geometry, which is that of a foliation. So when you have a vector field on a surface, you can integrate it, and it gives you a partition of your. I mean, you could do that with any manifold, though. A partition of your space into the integral curves of your vector field. So that's what we call the foliation. Foliation is anything that you obtain like this. Could be defined a bit more general way, but basically it's just you draw lines and you get a sort of dynamical systems by following what we call leaves of this foliation, which are the integral curves of that vector field. So now this is just for instance, a map where you have sort of a periodic leaf of your foliation and other leaves that tend to accumulate towards this leaf. So that should remind you of the periodic behavior that we've seen earlier. Okay, so what's nice about those dilation surfaces is that they inherit from the natural foliated structure of the complex plane of a family of the directional foliations. You have a foliation for each angle theta. So this is the horizontal foliation that I've drawn on this example. And some sort of extra structure that you have on this foliation, if you take sort of little transverse segments to this foliation, and you look at the first return maps for the foliation. So you just define a map by saying, I take this point and I map it to the first intersection point of the leaf going through that point in the future with this transverse map. Then what you get is that those maps are piecewise affine. And that's sort of what makes the connection with the one-dimensional dynamical systems that we discussed in the first part. Okay. And again, for those of you who are more familiar with translation surfaces, a dilation surface is just a generalization. It says that a translation surface is a dilation surface, but you've got some extra structure with a translation surface because you have length, and what was just piecewise affine in the previous discussion becomes piecewise translation. So again, many different ways to say that. Okay, so now I've got to introduce this particular dilation surface or bit of dilation surface, which are cylinders. If you take a cone in Euclidean space, you can mud out this cone of angle theta by a dilation of multiplier. That's why I call it rho. And what you get when you do that is something that's a topological cylinder, but since my identification have been made using real affine maps, what I get is also a dilation surface with a geodesic boundary, in the sense that the boundary follows a straight line in the complex plane. And well, these bits are very important because you're often going to see them embedded in more complicated dilation surfaces, and they're interesting in the sense that we can understand directional foliations quite well on these bits. So for instance, if you take any line that's contained within this cone and that goes through the origin here, well, it induces for the foliation in that direction a closed leaf, so periodic orbit for the foliation. And moreover, what you can say is that this is attracting, in the sense that if you take any other leaf in the same direction, but that's not the leaf that goes through the origin, then because when I glue the upper green line to the lower green line, I see some form of contraction. So if I take a leaf here, when I glue it back, it comes closer to the red leaf, and so on and so forth, and it tends to accumulate. So this is a sort of a geometric realization of those attracting periodic orbits that I mentioned during the first part. And so whenever I see a cylinder in a dilation surface, then I see some periodic orbits for the corresponding foliations, and I see some form of stability, because you see this red line. If I move it a bit, if I take an angle that's actually contained within the angle of the cone, then I see another periodic orbit for another directional foliation that is attracting it. This is just a way to see this the stability phenomenon that I was referring to earlier. It's a geometric way to see it. It's quite nice. It's quite nice. And yeah, so you have to bear in mind that those cylinders are important. So for instance, in the example that I've been using, here I can see a closed leaf that I got by the same phenomenon. So you have to tilt the picture to make the yellow lines fit into this framework, and you see that I have a whole cylinder that's swept out by periodic orbits, and I get a lot of periodic foliations with periodic orbits in an open set of direction on the surface. And they belong to two cylinders that appear here. So again, it's very nice when you see a dilation surface, try and find cylinders. They'll tell you a lot about the dynamics of the foliations. So what you have to bear in mind is that those cylinders, they act like traps, and they're responsible for some Morse-Mail foliations. So this concept of Morse-Mail, is asymptotically periodic, can be extended to foliations, where you say that it is Morse-Mail or asymptotically periodic if every single leaf accumulates to a nice periodic orbit. Not periodic orbit, I mean like cycle, closed orbit. Okay, so maybe this is an open question that I would very much like to know the answer to is, does every dilation surface have a cylinder? Or in other words, does every dilation surface have a foliation with a periodic orbit? We know the answer up to genus 2, so again, like very nice open question. Okay, so I just wanted to say a few words about the fine map that we'd seen earlier, and I said that there was some connection with geometry. So when you have a fine maps like this, you can sort of try and fit them into a dilation surface. And so I do here in this picture. So what you can try and convince yourself of is that you take the vertical foliation on this picture, on this dilation surface, where the identifications are the one suggested by the colors, or if you take the first return map on the segment going from the black side on the left side to the black side on the right side, then you will find this map. And now starting to tilt a bit the direction, then you will sweep out the entire family X map, X plus T, Tx plus alpha. So the one that we looked at earlier. And so there is this correspondence between parameter families of fine maps and families of directional foliation. So essentially, the theorem I mentioned, that almost every direction can be rephrased in terms of geometry in the following way. So almost every theta, you can find a cylinder covering that direction, and that will make for a periodic orbit, which will make for some Morse-Mail behavior, and then you have to work a bit, but essentially the theorem that I mentioned can be reduced to that. So when you have a dilation surface, you might want to define a measure of how dilated or wide it is, and this is what this function does. If I've got a dilation surface sigma, then I can define a theta sigma, which is the size of the largest possible angle of a cylinder embedded in sigma. Okay, so it's for those who know of the systole in like Riemannian geometry, it's a sort of systole for a fine stuff, which gives a measure of how dilated you are. Okay, so another question, which is completely related to the one I just mentioned, is does this theta sigma equals 0 implies that sigma is a translation surface? Again, I would like to believe that is the case, but it's still open. Okay, so that's all for this first video. So in the second one, we'll discuss parameter spaces, moduli spaces of such objects, and methods from SL interactions and Teichmuller flows that can help make the link between the dynamics of those foliations and those moduli spaces. Okay, thank you very much.